Finding the derivative of a function, knowing the values of the function at few discrete points, is fundamental in the study of computational fluid dynamics. I hope you understood that by now. In last few lectures, we have seen that Taylor series analysis can be used to prepare higher order numerical scheme. In this lecture, I'll emphasize that Taylor series analysis is an useful way to finding derivatives in general. Recall our definitions of numerical differentiation of the function u of x. We have learned forward, backward and central differences, and we know that forward differences are given based on ui plus 1 minus ui by delta x if we take the forward difference on 2 point stencil. Similarly, backward difference on a 2 point stencil is ui minus 1 by delta x, and central difference is ui plus 1 minus ui minus 1 by twice of delta x. In this particular course, by and large we will use first and second derivatives, but we will use not necessarily ordinary. In fact, mostly we will use partial derivatives. And the schemes that we will use, we will try to implement mostly in second order, sometimes maybe first order, but mostly in second order. And we will see that we can generate schemes based on the available points. We can generate schemes for derivatives using Taylor series analysis. Of course, there are other ways of finding derivatives, and we'll discuss one more in upcoming lecture. But you will see that this Taylor series analysis is the easiest way in general to find numerical derivatives. We'll illustrate this taking one example. Let us say we want to generate double derivative of u using 3 points ui, I plus 1 and I plus 2. Remember that we have generated double derivative of u based on ui, I minus 1 and I plus 1. We also know how to get first derivative of u based on ui, I plus 1, I plus 2. Here we are asking for second derivative of u based on I plus 1 and I plus 2. This is just to give an example that any derivative can be found using Taylor series analysis. However, to find a second derivative, you need at least 3 points. To find a first derivative, you need at least 2 points. You understand that just 1 point on a function is not sufficient to get a derivative, because derivative means change. So you need at least 2 points to know the change. And second derivative is change of change. So you need at least 3 points to get an idea of change of change. So here we expand ui plus 1 in Taylor series as ui plus delta x ui prime plus delta x square by 2 ui double prime, etc. And ui plus 2 equals ui plus twice delta x ui prime plus twice delta x whole square by 2 ui double prime, etc. So if I now write AUI plus BUI plus 1 plus CUI plus 2, we have AUI plus B multiplied by UI plus 1. We take this expression from the Taylor series expansion of UI plus 1 plus C multiplied by UI plus 2, and we take the Taylor series expansion of UI plus 2. Clubbing up the terms, we have A plus B plus C multiplied by UI plus B plus twice C multiplied by delta x ui prime plus B plus 4C delta x square by 2 ui double prime, etc. As we are trying to express AUI plus BUI plus 1 plus CUI plus 2 as UI double prime, our goal now is to make A plus B plus C equals 0, B plus twice C into delta x equals 0, and B plus 4C into delta x square by 2 equals 1. From these three equations, we should be able to find these three unknowns A, B, and C. We find here both A and C are 1 by delta x square and B is minus 2 by delta x square. B plus 8C, this is necessary to understand the accuracy of the scheme, is 6 by delta x square. That means the coefficient of ui triple prime, that is b plus 8c into delta x cube by 6, is actually delta x. So the truncation error is delta x multiplied by ui triple prime plus additional terms. Therefore, I can write now ui double prime is equals ui minus twice ui plus 1 plus ui plus 2 divided by delta x square plus truncation error, which has the order of delta x. So this is a first order accurate scheme. This is 3-point forward difference scheme for double derivative. 3-point forward difference scheme for single derivative is second order accurate, but 3-point forward difference for double derivative is only first order accurate. Why do we need this? Well, sometimes we need double derivative at the left boundary of a system. And in that case, we can take double derivative only via forward difference. But we see that this double derivative is only first order accurate, so we have to live with that. If we want to make it higher order accurate expression, then we have to bring additional term. If you want higher order accuracy scheme for forward difference double derivative, you can take ui plus 3 in the mix and try to figure out if we have this expression of ui double prime equals a naught ui plus a1 ui plus 1 a2 ui plus 2 and a3 ui plus 3, then what will be these coefficients a naught a1 a2 and a3, and what would be the order of accuracy of this scheme? We certainly expect that it will be at least second order accurate. So you can try this exercise and see what will happen. All the discussion that we had so far are contained in the chapter 3 of your textbook. So this will be a good time to go to your textbook and read this chapter. That's all for this class. We'll see you in next lecture. Thank you.